Welcome to the module on coordination chemistry. This is the module that explains all the beautiful, well, not all, but a lot of the beautiful colors that we see in chemistry. So, if you recall from last week's lectures, we talked about or we introduced complex ions, which are also called coordination compounds, which are also called coordination complexes. And many of them have transition metals in them. So here are some examples of transition metals in different complexes that form these beautiful colored crystals here found in nature. If you're interested, you should look up the properties of these different crystals. So the transition metals are found in groups 3 through 13 of our periodic table of elements. And these transition metals here make up the D block. So the electrons in these metals actually fill up the d orbitals. There are five d orbitals, meaning that it can allow for up to 10 electrons. And then this inset here makes up the lanthanides and actinides series of our transition metals. And these are the F block elements that can allow up to 14 electrons. There are 7 F orbitals. So what's really cool about transition metals is I like to think of them as like the shapeshifters, right? And I call them shapeshifters because you can take the same metal and under different conditions, right? And by different conditions, I mean if they're in a complex with a different ligand, they can have a whole new set of properties, and we'll talk more about this. So the reason that they are these shapeshifters is because many transition metals can form compounds with varying oxidation states. So here are some examples of different transition metals and all of the oxidation states that they can adopt. So looking at an element like manganese that can have up to 5 different oxidation states, right? And under these different oxidation states, it'll have different stabilities, different like spectroscopic properties, different magnetic properties. So they're really cool in this way. And because of that, they have a lot of different applications. They're found in different forms of nature, and there's a lot of different applications for transition metals. I mean, like from technology to drugs to materials that we use, lots of applications. Let's do a review of electron configurations. Boom, 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 boom. It's review time, it's review time. So this picture here is from a figure in chapter 6 of the OpenStax textbook that all of you have been reading all along. And I really like this figure because it diagrams how the electrons feel the different orbitals. So last semester you mostly talked about the main group elements that fill the s and p orbitals, and the transition metals fill the d and f orbitals. So here are two examples of transition metals. We have chromium 3 plus and gold. So pause this video and write the electron configuration for both. Hint, for chromium, well, before I say for chromium, the general steps, look at the periodic table, look at its atomic number. Whatever its atomic number is, that is the number of electrons. So we can check that when we write the electron configuration that we have, essentially writing the electron configuration is like writing or depicting the home, like where each of these electrons reside, right? So you can count the superscripts to make sure that all of the electrons have a home, right? Now with chromium, because it's 3 plus, that means that it has 3 less electrons than chromium in its neutral state. So once you write the electron configuration for neutral chromium, then you're going to subtract 3. You're going to subtract 3. For gold here, it's in its neutral state, so you're just going to look at the atomic number, which is the number of electrons, and make sure that they all fill the orbitals. So pause this video and give it a go. So here is what you should get for chromium 3 plus. Chromium 3 plus. So when you add all these superscripts, it should equal whatever the atomic number of chromium is minus 3. And recall the shorthand notation, we can go to the nearest noble gas and just write that in brackets, and then from there write where the remaining electrons go. So we could write argon 3d3, 3d3. Here's the electron configuration for gold, the longhand notation, as well as the shorthand notation. And so gold is in the F block of our transition metals. So here are some examples of transition metals that are found in nature, in jewelry, for those of you that wear copper, gold, or silver, copper jewelry as well. And we're going to talk a lot more about copper when we get to, or really all of these, copper and gold when we get to electrochemistry. But what is really cool about copper, for example, and gold, they are really conductive. So I'm going to attribute that sound to fireworks nearby. But yes, back to what I was saying. Copper, gold, silver, transition metals that are found in nature that are like heavily revered and sought after. Well, especially gold specifically. And I was sharing how they are conductive. Conductive meaning electrons can flow freely through them, and we'll talk about this or come back to this again when we are looking at electrochemistry. So, in addition to being found in nature, transition metals also have a lot of applications in technology. So, europium is used in display screens in our technological devices like computer monitors, cell phones, and televisions. Neodymium magnets are commonly found in computer hard drives. So two examples of technological applications of two transition metals. Another example is iron. Molten iron is used to cast or make steel. And another example is where there's superconductor technology used for a magnetic levitation train. which is really, really cool. I'm not sure where this train is found in the world, but superconductor technology is, I mean, that's a really heavily studied area. And if you were to do research in this area, for example, you would become very intimately involved and engaged with transition metals. So, what is the reason for the beautiful colors that we see in these complexes that have transition metals in them? It turns out that transition metals with partially filled D subshells usually form colored complex ions. But if the transition metal ions have an empty D shell or are completely filled, a completely filled D subshell, these usually form colorless complexes. So here I am showing 6 different transition metals that are in complex with water molecules. And we see that scandium and zinc, right, form this partially, not partially, I'm sorry, empty D shell and completely filled D subshell, which is why these solutions are clear. Whereas chromium 3 plus, cobalt 2 plus, nickel 2 plus, and copper 2 plus in complex with water molecules form these partially filled D subshells, D3, D7, D8, and D9. And that is why they form these beautiful colors. These beautiful colors. So, how the electrons occupy the D subshells contributes to whether or not we see these colors in the complexes that they form with ligands, or if we see a colorless or clear solution. So, the reason for the colors is how the electrons feel the D subshell.